Prusight has been in an industrial automation space for the last 5 years now. We have solutions ranging from predictive maintenance technology, condition monitoring, energy management, and visitor management. Without wasting much of our time, I would like to introduce Mr. Prashant. He is a product manager for Prusight, a highly efficient leader with over 12 years of experience, responsible for the product planning, execution throughout the product lifecycle, including gathering and prioritizing product and customer requirements, defining the product vision, and working closely with engineering, sales, marketing, and support to ensure revenue and customer satisfaction goals are met. Post-webinar, we will be open for the session of question and answer discussion. If you get any questions during the webinar, you can drop your questions in Q&A button. Thank you once again. And now over to Mr. Prashant.
Yeah, thank you, Nidhi. So hello everyone, this is Prashant here. I'm one of the product managers at Prusight. So today I'll walk you through about machine vision. So a lot of you might have an understanding of machine vision, or some of you might use machine vision system on a day-to-day basis in one of your facilities. So this will be an introductory session. We'll walk you through what exactly is a machine vision system, what are the types, technicalities associated with that, and how specifically some of these industries are using machine vision and getting business benefits. So it'll be mix of technical as well as some of the use cases details. So you can always drop your questions on the Q&A section. Whenever you have a question, we can pick it up in the end of the session, or my teams will address it the chat during the webinar itself. Yeah. Having said that, so just a quick background about who we are, what we do. So we are primarily an automation company focused on manufacturing companies. So we work with many companies within India and help them with their automation requirements. This is specifically in factory data management, factory automation. We also work on many Industry 4.0 sensor related predictive maintenance use cases. So just to start with today's topic, what exactly is machine vision? So from a definition wise, vision basically refers to the image data set which hardware generates. So in most of the cases, the image is generated through camera. So the camera generates or captures a particular set of image. So using that camera, we can use that particular data and interpret that data if you look at from what you have in your factory, but technically it basically is a non-contact approach where the camera is far away from the product, from the process, from the scope of the particular subject, and it collects data in a non-contacted way and then interprets that. So that's what we do. So we can connect that output of the data in and analyze that using algorithms. You can just use it for archiving. We can also connect that directly to a machine, so the machine image is captured. So we will go through those use cases, but in a nutshell, image data is used, and it is used to used for computation or used for other processes. So the evolution, again, this is from one of the leading manufacturers of sensors, Cognex. So they have a very detailed evolution because they are one of the earliest players who manufactured a component called Dataman. So from a proprietary box where the camera used to be connected, so today we have wide variety of sensors, doing multiple resolution, multiple speeds. So in the initial days, it was take a photograph, connect to the camera, analyze it. Then we had built-in embedded boards, which was basically able to capture the information, which is the image data, and process that at the board level itself. Very basic level identification. Then we had the PC. Now we have very modular ones. We can have handheld devices, and now there's a lot of computation that the camera itself. So it can sense, it can calculate, it can do a lot of 3D, and so this is where the machine vision as an evolution has happened. But what exactly it does, what is the purpose, is basically we look at binary data, which is the image data, and look for an answer. We look for a decision to make. We look for, where exactly is the location in that particular image. So these are the fundamental use cases or purpose of a particular machine vision system. So this boils down to multiple use cases. But when you look at system itself, so there are multiple components. One is the camera, which is there positioned in a location. We are looking at a lighting system. So lighting is very critical. I'll also talk about the types of lighting in a while. We also have the sensors, and that data is captured, is moved to PLC, which is logic control, and then in the software level, we are able to analyze all of this information. There's a lot of controls given to users, but multiple components are involved, and they all work in a seamless way, in a real-time fashion, at a highly effective way, where multiple objects are analyzed in a second basis. So some of the examples is like, if you want to look at alignment, if you want to look at the spacing, in this case, we just want to understand, okay, whatever is the distance between this bracket, or we want to understand if there is an issue with the oil filter, right? So these are the kind of preliminary use cases where you can identify in your factory, in your processes. A small camera can do it. So multiple times we have to feed the camera, we have to take the data, but it can be just to capture the data or gauging purpose, or to inspection purpose. We can use machine vision. So let me just talk about the types of machine vision systems. So there are multiple types of machines. So the first one is a 1D, one-dimensional system, where the object is going on a particular surface, and the data is captured, and based on that, a decision is made. So single dimension, one particular area is covered through the camera, and the data is collected. Similar way, we have 2D vision systems. So we have the 2D vision systems basically look at the particular data points from the object, and they recreate the entire the second dimension in a digital way. So if the camera is going, and this is a shaft on a conveyor, and the product is going this way, so it basically acquires one line of data, but over a period of time it builds a series of images. So complete 2D image can be built using a combination of the line, frame grabber, as well as the sensor. Similar way, we have 3D systems. So depending on the use case, you can actually use a 3D camera itself. So this can be a single camera, this can be multiple cameras, multiple 3D cameras to get the baseline 3D, or you can actually triangulate. You can have multiple cameras to triangulate and then feed that data to create a 3D modeling kind of use case. So single dimension, two dimension, and three dimension, depending on the use case, you can actually go for these kind of vision systems. Next is what are the primary scope of these mission systems are basically, they look at dimensional aspects, they look at structural aspects, they look at surface aspects, and the operational aspects. So dimension in the sense shape, positioning, orientation, alignment, roundness, corners. If somebody is manually checking that, you can outsource all of that to a camera. Same way structural, if you are looking at finishing like holes, rivets, screws, any of these structural changes to a product level, either verification, or just to see the alignment of it, or to calculate the dimensions. So all of that can be done. In the same way, from a quality part, you can look at the scratches, wear and tear issues, finishing, roughness. So those kind of issues, the cameras can actually grab in a faster way, almost in a real time, and at scale. And even the operational issues. So if you have specific standards, specific alignment, particular dimension criteria, you can feed to the system, and the system can actually capture that particular information. Let's look at the common use cases. So basically, looking, so predominantly the use cases are classified in four types: guidance, identification, gauging, and inspection. So guidance is identifying the particular specified tolerance, what you want to have. Very very entry level, I would say, machine vision use case, because using the guidance data, most of the times we send that guidance data to some other subsystem, and the subsystem basically uses the guidance system data and takes an action. So it can be a robot which can be turning, or it can be again finishing. So a lot of the identification is also already covered. Some of you might have barcode systems in your factories. Some of you might have QR code systems in your factories. So all of that covers the identification part. Next is gauging, so calculation of the values itself. Next is inspection. So again, in terms of guidance, you can look at any alignment or in any part. If you want to specify, or get some details. So you can actually do that, and this is done at a very high speed level, where workers don't have to, supervisors can actually look at the data, confirm it, or it can only flag if there is an issue. Similar way again, you can also do pattern matching. So these are advanced machine learning techniques where either the orientation is different, or if the polarity, or any different background, we can do multiple ways of pattern matching for the guidance use case. Similar way for identification, you can read all barcodes, 1D, 2D. I mean, tomorrow if there is a new barcode, this is an advantage with camera based vision system. So you can easily train to read the particular barcode, and you can also allow it to recognize characters. So there are two ways. One is optical character verification and optical character recognition. So in the OCR, it tries to read the data, and verification is basically it just matches or confirms the particular string. Yeah. So next one is gauging. So I already talked about this. Yeah, pretty much. You look at the distance of couple of points, geometrical positions, and it try to matches that with the system configurations, right? So it's kind of basically getting the information and verifying that with the system configuration details. Similar way, inspection. So inspection is again looking at a specific use case we have classified as a defect, or any variance to the good use case. So we what we would have mapped in the library, it tries to verify that. It compares every single data set and flags this as a defect or not. So there are multiple use cases. If you have any product or any specific use case, you can actually train, create a set of defects. What are the possible defects if you have a knowledge base, or you can define what is your positive use case, and the system will only try to compare with that. Any variation with the positive use case, it is flagged as a defect. It can be raised as a ticket. You can basically collect that data and use it for processing. So let's look at the goals. What are the goals associated with this system? So how, if you are looking, okay, I want higher quality in my factory, you should invest on a machine vision system for inspection, measurement, gauging, assembly, and verification. Same way with respect to productivity, you can if you want to increase productivity in your factory, you should basically invest on a machine vision system where people are doing it manually, like somebody is manually verifying it, somebody is manually checking or manually scanning the barcode. All of that can be replaced by a machine vision system. Same thing with production flexibility. So if a robot wants to do it, but every time the robot is being fed data, automatically the camera can feed data to the robot. So those are the kind of automation you can do by adding machine vision system. Next is again reduce the downtime. Again, this can be programmed. You can set configurations, time-based configurations, environment-based configurations. You can also add more tighter process control, because all of that data is coming from the camera side. The data is directly converted into a digital format, and that can be fed for very real time information of the floor. Also, the capital investments are lesser. I mean, when you look at the kind of performance it can give, so if you want to reduce capital expenditure on the equipment, you can combine with some cameras, and not necessarily need a new machine, but control it through the camera itself. Again, some of the other advantages with respect to production cost or scrap reduction, inventory control, and reduce floor space. So all of that basically talks about how machine vision system can replace existing personnel, in terms of your QA, or again, the beauty is the scalability is built in. So if you have 10 use cases in your factory, it can be processed by a single server. You don't need 10 people to do that job. So you can have 10 cameras, but centrally analyze it through a single computer. So that can be an easier way, and it can reduce significant cost. So let's look at a key element of uh, you know machine vision system. Without lighting, the camera camera can actually basically interpret the data, but what exactly is it seeing? So that depends on the lighting aspect of the particular object. So lighting is very critical whenever we want to implement a machine vision project. So because depending on the kind of lighting, the product change looks differently for the camera, and based on that interpretation, probably we can classify the defect or inspect, do the inspection in a much uh, faster way. So it can be color, it can be surface properties, it can be the geometry aspects of it. It can be, sometimes, the features we are interested in. It can be, uh, also the service life of the particular lighting device itself. So these are the core specifications. Let me go through one by one how exactly these specifications are interpreted. So if you see the type of appearances, so object which is normal can appear wider, higher, distorted, in a non-linear way, sometimes rotated for the camera. Same way, it can have something in the background. It can have it can be visible in a very incompleted way. Sometimes the camera is not focused, or there's a lot of particles in between, something like a dirt, or it can appear much lighter, darker. So lighting plays a very important aspect to reduce these kind of appearances, and always, like, in every angle the product has to look similar way. So we can do backlighting for the use case where the object is there, and behind that the light is projected. So this is helpful in some use cases. Next is diffuse lighting, and if the light source is cutting through the camera, and it illuminates in a different way through a mirror. Next is a structured light. So we have a fixed light, but it's coming at a particular projection for the particular object. We can also do dark field illumination, two sources, and targeting on a particular object, and the camera is basically looking at. So they all have multiple types of image. So depending on what kind of use case we need to identify, so it depends on the field of view also. Yeah. Same way, bright field illumination, where again you have any high contrast applications, you can actually use this, and then it creates consistent illumination in the field of view. Next is the dome lighting. So you can have a mirror finished lighting where light is created in a dome kind of structure, and then it falls on the particular object. So there are multiple light sources also, depending on the use case you can actually use. And if you're looking at the strobe or the intensity, the life cycle of the particular light, or in terms of the cost, there are multiple options available. This needs to be seen in where exactly we want to solve the machine vision use case. So some are applicable, like LED fits good for most of the use cases. But if you're looking at laser, or if you're looking at halogen, so it is very specific to the particular use case. So let's look at building a vision system. Basically how we can incorporate a system in a factory, or what are the terminologies, or what are the processes which is involved. So the first part is basically identifying what is the scope, in terms of next is identifying the design, and next is calculating the cost involved in the particular project, and how can we deploy this, how can we install this particular system. So these are the key elements of any vision system project in your organization. This can be at a unit level, this can be at a plant level, So the scope of a system is what you want to see, right? And what is the vision system should see. But sometimes what you really need to see is more important versus what this camera can see. So we are looking at a entry level camera, so it can basically look at few data points. If you're looking at a very fast sensing camera, so then another use case is much different. So we should also see what are the limits of this particular camera, or what is the scope of this particular system, what it can identify, what it cannot identify, and the kind of components, the light sources, and advantage, disadvantage. So this the scope is critical before you implement it. The next is to identify particular designing of the system. So what kind of camera needs to be there, what kind of field of view, what is the resolution, what is the kind of lens. So lens is again very varied. It depends on the use case. Then we need to select the camera model, the type of illumination, and what are the mechanical endpoints, like can it be screwed, can it be mounted, and what are the electrical interfaces, what is the voltage level is available at that point of time. And then the next part is the software part. Is it available on a phone, is it available on a desktop, or is it available on a network, all those kind of integrations. There are multiple parts of a particular vision system. So what are the color finishing, if somebody touches it, if there is a fingerprint, should it ignore, should it not ignore, what happens if there is a change in shape. So all these parts needs to be documented as well. So once we do the document, we need to understand where exactly we're going to put the system. Is it in a natural light? Is it in a, are we going to do we have sufficient lighting conditions? What are the temperature ranges in that particular area? Is there a shock, vibration, dirt, or dust? If there is a kind of protection or casing provided for this vision system, and also availability of the power supply. So these are critical part. Next is identifying the camera itself. The camera, what is the model for the camera? What is the interfacing technology? So there are multiple formats, data points like camera link is there. Some of them are proprietary protocols, some of them are open protocols. So you need to identify what is the interfacing technology with the camera. Again, the packaging size and the price points, what these cameras are available. So you should also look at what is the scan direction. Can the camera move, or does it have a rotatory mechanism built in? Then we should look at the grabber. So this is uh, also an important part where it takes photographs. What is the pixel rate it can take, and what are the software libraries associated with that? How many cameras this particular grabber can work with? Then we need to look at the timing aspects of it. If there is a onboarding, if there's a hardware enabled processing, what are the API integrations available with the frame grabber. Next is again the software part. Once you get the data, you need to crop it, measure it, or do some pre-processing. After that, extraction, localization, interpretation of the software is important. You need to also look at the result generation mechanism. Is it gonna give a API data? Is it gonna be XML or a flat file, CSV data? So you need to look at these interfaces as well. Again, you need to look at the computing infrastructure. So the computing infrastructure is, are you going to put it on your factory data center? Are you going to put it on the cloud? Are you doing a hybrid model? You can also look at what are the memory level, processing speeds. You want to do it real time, or you want to archive everything, then process it at a later stage of. So again, the algorithms. So if you have hardware enabled algorithms, or if you want to look at uh, basic operating system like Linux running a TensorFlow or a Keras, or you want to use GPU based processing. So multiple aspects needs to be computed in terms of the API, what it integrates with the software part. The next part is the cost. So cost is again, pretty much on the hardware side, the software side, the computation part. It also depends on the training and the feasibility test. Many times we have seen with customers, like we assume for a camera use case, but once we test it out, probably they need a higher resolution. So there has to be a test run, and once the POC, proof of concept, is done, then the final installation, training, documentation is done. So again, in a nutshell, you can easily go live with a machine vision project with some specifications documented related to the use case and a detailed development and installation part. Obviously, testing it out. Then once the acceptance is done, the system goes live. So sample specifications, how you can actually say, hey, this is my particular machine vision system. This is the use case for it. So you need to define the task and benefit. So what is the task the camera will do? What is the benefit the business gets? So this is critical for all machine vision projects, where you need to say, for this component, this is the task the camera should do, and this is the benefit it has to incur. So it can be, again, in this case we're talking about a rivet, specifications of the rivet, what are the accuracy level the camera should detect. So you can document like this: what are the tasks, what is the benefit, what are the parts involved in it, and also what is the installation space where it is going to get installed. And the same way, what is the part positioning, like how the part is kept, and if the build stops at a so and so period of time, the vibration is so and so. So you need to document all these components in order to even scope a particular machine vision project. So next is, what are the performance requirements at a camera level? So you can declare all of these on the software, but from a product level, even before you buy any camera, you should identify the part positioning and the performance requirements, and what are the information interfaces, right? I mean, what is the electrical availability and what kind of data you would like to see. So that's critical when you design a particular machine vision system. So let's look at some examples. We have explained what are the types available, how we can actually do it, but let's cover some use cases with respect to industries. So for food manufacturing, again, I can do fill level manufacturing like cap closure, ring, label positioning kind of use case. The image is taken, but you can actually classify every single component in the image. Okay, I want to look at this particular data. So this depends on the illumination part. So there are multiple use cases from various manufacturers. I'm showing. It depends on the camera specific use case. Here in the case of they're doing gauging. So with respect to packaged food, this is the product dimensions. So they're doing gauging with the image of the product. So they want to keep the product within the space, and the camera is actually taking the photograph and doing a real-time calculation of it. So it's straightforward. The image is taken and the gauging is done. Next is, again, packaging inspection. So if you want to identify the package, and any edges or any issues with the camera. So again, if here the image is again modified, right? So the like kind of lighting chosen here is different, and the kind of photograph which is taken is different. The kind of processing is done is different. So lighting is key, and then the camera, and then how we basically analyze that particular image. That is more important. Next is label inspection. So if you want to do any specific use cases, so cameras can be very helpful here. And if there's a wrong label, it can identify. You can train all these use cases within the system, and it can identify or read the particular information, even the contents of the particular label. It can basically do that. Next is seal inspections. If you are looking at any seal in any of your product, it can do that. Similar way, again, if you can identify defects, or any issue with the sealing part. So it can do that microscopy observation in a fraction of time, and you can do uh, any kind of grading for this, either a robotic arm, or you can do manual picking. So you can connect that to any data point. Next is, again, you can have any custom checkpoints, not necessarily the camera identified, but this requires some training. But you can basically map it for custom checkpoints or custom specifications. Okay, the sealing is not proper. If there is a foreign material in that particular area, any foreign material or any changes, if there is even like less than 95% score for this particular area of the image, it's kind of a defect. So you can basically declare that way, and the system can flag defects. Next is, again, grading. So most of these agricultural produce already have dedicated grading systems, but even if you have any custom component, you can do a combination of 2D, 3D cameras, and basically do the grading. Yeah. Let's look at pharma examples. What where typically machine vision systems are used. Again, this is again with respect to some of the checkpoints. If you want to look at for boxes with leaflet is being inserted, or anything damage in the blister packs, or label position. If the label position is accurate, or if you want to read 2D, 3D barcodes at scale, you can use. Uh, Again, these are all kind of custom checkpoints. So again, barcode labels or text detection within the film. So here it's reading the text, but there's an obstruction, which is the film in between, or it can be again, barcode readers on a shiny surface, curved surface, because those, again, the illumination matters here. It can read from any surface, so we need to train the system. We can also check for the safety seals in the bottles. Let's look at again for solar panels. So this is for solar panel manufacturing. Again, just an example of how what is the depth this can go. So it can be chip detection or a pinhole detection, back print or detection in both the cases here. Similar way with color uniformity, crack detection, front finger here, the trace detection, and the bust film detection on the top. So multiple use cases. You can train the image, and it can basically identify in real-time basis. Next is for garment manufacturing. So again, this can be the cloth condition, cloth-based effects. We can basically do in real time using cameras. So this is what we have done for a Bangalore-based customer. Again, cloth, denim cloth was layered. We used to use cameras and take multiple photographs and compare that to a CAD file, and basically, get that information. So here the cameras are taking multiple photographs, and the image is stitched together. The stitched image is checked for defects. So these are the defects we got, and that is superimposed with the vector file, which is a cutting file. And now we get a list. Okay, in this cutting component there is a defect, you can replace that cutting component. So it's again image with all the defects. So here the markers are there, the defects are identified, and the defects are superimposed on the CAD file. So now when the cutting is done, we basically replace these items. Earlier it used to be manually inspected before it goes to finishing or packaging. These cutting pieces used to go and they used to get rejected there. Now uh, we in this case, workers manually pick this. It is not through a robotic arm, but the use case implemented, and everything is controlled through a tablet. And it lays multiple layers of fabric. So every time a layer is laid, the camera automatically knows a new layer is laid because it's watching the moments of the layer. So some use cases for electronic manufacturing, again, it can be looking at the PCB verification. This can be specific components associated. This can be individual components spaced correctly, or this can be very cosmetic inspection kind of activities. So if there is a scratch, there is an issue, so this can be flagged easily. So again, this can be for any component in your factory. Today somebody's manual checking, so that can be replaced with a camera and some basic training. There's a cosmetic inspection part again. uh, any cosmetic variation, it can automatically take photographs and flag these defects. We can set tolerances for all these defects, and depending on the tolerance level, it can basically flag that as a defect. So let's look at deep learning. So what we saw is cameras taking photographs and processing that, but machine learning has improved, and there are so many new algorithms available which works in a very local environment with reduced infrastructure. So using deep learning techniques, it can go to a very micro level at a pixel level and relearn that. It get trained in a hierarchical way on the same image. So can basically identify a combination of objects in a very easy way. So the way image recognition used to work, comparison way versus a deep learning way. Deep learning is continuous learning, so any new defect is also can get easy classified, it can get trained, and the more accuracy it receives, over a period of time, the accuracy increases because the newer results are also being getting part of the training library, and the model is generated very frequently. So there is no fixed model, and it's always continuously learning. So there's a difference between machine learning, where we basically do boundboxing. We tell, hey, this is what this is, or this is what a defect is, and then the output is generated. So in deep learning, the feature is extracted, the classified at algorithm level itself. We control that through algorithms. So once the training is done frequently, the output is improved. So that's how the deep learning models work. And there are multiple ways it can understand and predict the particular uh, responses. So let's look at some of the algorithms which are generally used. So this can be for image transformation, geometrical manipulation, content statistics. We can also use deep learning for image enhancement or pre-processing, connectivity. So if one line has to go from here to here, those kind of mappings, we can do it through deep learning. We can also do it edge detection, correlation, geometric, OCR, character recognition, or character verification and color processing. So all of these can be done via the deep learning algorithms. So there's also a comparison. People frequently ask this. So hey, why not I go with a barcode? If I barcode is my use case, why don't I go with a laser-based barcode reader itself? Why should I go for an image reader? So there's some advantages, which is again, image is controlled through an algorithm, which is much more easier to tweak and add. So laser-based systems are good, but if you are looking at a long term, the read rate performance and multiple uh, products to be compared. So image-based recognition systems are much better than laser-based reading systems. So this can be again omnidirectional. It can read from any direction. This can be in terms of the reliability, visualization, even the archiving is there, which is not available on the laser-based systems. You can have a complete detailed time log of why it was classified, what is the confidence score, and it can basically create multiple reports and dashboards associated with that. Again, some kind of future proofing is there. So if there is a comparison, if there is a question between a laser based system and an image based system, you can always invest on an image based system, on any basic algorithm also, because software can be controlled, can be upgraded easily from compared to the hardware part. So let's look at some of the leading players who are there and who manufacture these systems. So Cognex is, industry leader in this space. So there are multiple varieties of industrial sensors, cameras. So it can be from 2D, 3D. So they have multiple high-speed resolution cameras. They manufacture multiple cameras, and they have their own software suite as well. It can be connected to multiple use cases. Again, can be dimensional, 3D, gauging, inspection kind of use cases. So then there is Kians. They also similar to Cognex, multiple use cases. They do color code, color processing, color distribution, much easier way. Then we have products from Omron, which also similar to Cognex. So multiple product portfolio for all kind of use cases. This can be for contamination check or any kind of circumference check at a very millimeter level. They can actually do this and generate the results in real time basis. Then there are specific components from Zebra, which can take multiple photographs or it can do multiple barcode reading in an inventory kind of environment in a much faster way. So we also have components from Basler. So they also have depth sensing cameras, for primarily used for fast moving use cases, 3D scan kind of use cases. If you have components, you want a 3D scan. So there are multiple components available from these organizations. So again, we also have a solution, but primarily on the software side, where we basically extract data and connect that to sensors. So it basically identify. You can map out device. You can bring any camera which you have, or any of the manufacturers which you showed. You can take their data, and we basically take the data to the next level. help you automate, create alerts, and a bunch of reports and notifications on top of that data. So let me just quickly give you a small walkthrough of what defect site would do. So again, we have the camera set up. The camera is giving the data to a gateway, and we'll be able to show that data on defect site. So in this case, we are basically looking at stain, dust, scratch, hairline kind of activities. So if you implement defect site with any of these cameras or any of your existing cameras or even a basic camera like a web camera, you can basically identify defects in a factory environment. So you basically look at the stains. We do a feature map. We store that data internally, and then we hand out the result every time we do a particular image. This is what we do. So we have a small video to play across. So in this case, we are basically training the photographs, and the images are shown like this. So this images are trained within the system. So in the interest of time, I'll just play back. So once these images are added to the solution, so you're basically training these images for the first time. So all these defects are there. We are training these images. We are labeling them. What type of defect this particular uh, defect is, and you can do a lot of bound boxing, editing of this particular defect. So once a defect is done, so we will so the list of labels are added. So it is trying to train the system in this case, and the defects are done. So once the defects are trained, basically, what you see here is the list of defects and the kind of dimensions it has for x-axis, y-axis. So it basically gives that particular list of labels over here. So those defects are taken and then used for algorithm purpose. So which we'll see in the next one. So in this case, we will we are using the same defects, but we will be able to run the defect. So in this case, this is a PCB. We will run the defect algorithm on top of this. So the moment we run the algorithm, it is able to flag two defects, and it basically gives the detailed timestamp of the particular defects associated with the product. Yeah, so these are the defects. You can see that information. And this data can go back to a task management solution, or you can archive it. All of that can be done. So you can connect this to any camera. So in this case, we are probably doing with a very low end camera. So either you can go for a industrial camera if the use case needs it, or if you want to do very cosmetic inspection, you can use a solution uh, like ours, and basically get those defects in an easier way. And this data can go to a QA system where you can attach that to a workflow, and they can mark it complete or not, or you can control it through a smartphone or a tablet. All of that can be done. But the training is very straightforward. It can be done in a very low computing environment, and the detection can also be done in a very low computing environment. So in this case, we're just taking out the data, the defect log, and the defect log is generated as a CSV. And we also have an integration with our own software, but for this example, just showing it through a CSV file. Yeah. Multiple defects are captured. I'll just run through this. Yeah. So you've seen the system, you've seen some of the industry examples. Now, if you want to buy something for your company, how is that you're going to evaluate? So you need to basically look at what are the operator interfaces you would like to have, what are the vision system networks you would like to create. So you need to have, and how is that basically manufacturer will help you with that. You should also look at the part location tools, how you want to access the performance, what are the part components, for the vision manufacturing setup. And you should also look at why would you, I mean, what kind of functionalities the vision system manufacturer or provider is doing with image pre-processing, because pre-processing is critical for us to increase the accuracy. And it should also look at capabilities like, can it read characters, can it recognize characters, and the next thing is, what are the gauging tools available. Some of them are very inspection tools, but gauging helps you understand why that inspection is valid, or if you want to do for any physical object, so you don't have to buy another system for gauging, so it should be covered within the same system. Next is, it should look at industrial code reading. So this can be barcode, QR, or multiple, code reading terminologies, and what kind of API is available. This is again, is it a proprietary protocol? This is an open protocol. So that is important. And once the software and network is covered, you need to look at what kind of accessories, in terms of cabling, in terms of capturer sensors, what kind of accessories are available. And again, the hardware provider has any set of options, and are they safe, are they rugged, are they compatible for the environment, either a heating environment, cooled environment, or regular conditions. Magnetic interference is there, vibration is there, so multiple things needs to be thought through. And then you should also look at, what are the support and training services you would require to get started on this. So that was my time today. So what, I think it was, a lot of information for some of you. So if you want us to basically come and say, look at your process and give out, an audit report, we are doing that. So you can reach out to us, and you'll come to, see your, I mean, we'll virtually see any of your process. We'll recommend, can it be covered through a vision system? If so, what is the components, what is the, a budgetary cost for that vision system? So we can, deep dive into one or two discussions with your teams directly, understand the use case, what you want to cover with camera. Is there a camera available for that? Is there algorithm available for that use case? And we can hand out a report. So that is something we are doing. Even if somebody is watching the recorded version of this, you can always reach out to us on the website. There's a contact page form, or you can send a mail to audit@prusight.com. Yeah, I think we are good for now. If you have any questions, we can take them, Nidhi.
Yes. Thank you, Prashant. If there are any questions, please place your questions in the Q&A button. Prashant, we have one for now. In terms of matching samples via teaching by vision system, what is the tolerance band?
So in this case, from some of our examples, we have set around 80% and above. But this is configurable. So generally, we keep it around 85% and above. Yeah. Depends on the coloring, lighting conditions, but if it's product, or if it's, a pre-processed image, it can have a high range value because the image is already going through a pre-processing image. Most of the cases, there is no raw image, so the tolerance levels are always higher for pre-processed images.
Okay, thank you. How it helps in less machine downtime and reduce changeover time?
So again, some of the components, in terms of, let me say, you have many mechanical components, which cannot fit in a sensor. So you can put a camera and continuously monitor that. Every time there is a, movement of the particular component or any variation in the component, you can actually, flag that as a defect. So predictive maintenance is useful. In many cases, we might not have a proximity sensor available, we might not have a temperature sensor available, uh, because of how the machine is connected or situated, or the dynamics of the machine. So a camera is always a non-contact sensor. So if there is a way we are able to sense anything related to a machine, either a movement of a screw, or to, some gapping, or uh, some kind of visual change. It can be in terms of rusting, corrosion. So all of that, if you think, a camera can do that, we can basically use that data. The camera will interfere, right? Okay, it identified corrosion in the particular machine, then somebody needs to act. So prediction use case, predictive maintenance is easily connected. It depends on the use case. In some cases we have seen in terms of the conveyor belt, right? So conveyor belt being continuously monitored by a camera. So any wear and tear automatically identify any misalignment, automatically it verifies. At a high speed environment, it can do. And the moment it is something about to happen in a precautionary measure, it can actually control the speed of the conveyor. We have implemented that use case. So in predictive maintenance, it is definitely helpful. We need to understand the use case. What is a critical equipment you would have, and then try to identify image specific use cases. Yeah.
Thank you. Next question is, I need to identify the life of LED based on glow and temperature observed. How will that be done?
LED is the product.
Yeah, life of LED based on glow.
Yeah, so Ajay, this was a question that I was answering previously. So this is a follow-up question. So I think we will discuss with him separately on his use case and understand his use case better.
Okay,
So he wants
please.
to identify the lumen of the LED bulbs and compare it with the temperature and the applied
Okay.
voltage. So we will discuss this use case with him separately.
Yeah, I think somebody can collect their contact details and we can reach
Yes,
out.
we'll do that.
Yeah.
Yes, thank you. Uh, it helps inventory control. How can you please explain about it?
So inventory control, again, if somebody is going and scanning barcode details, you can place a bunch of cameras aligning to those rows and shelves every time somebody's picking and putting it back, or any movement in inventory. We can basically control that. There are very new concepts like cashierless stores where a combination of data is then, but that's at a retail level. So but at a factory level, either you can have multiple cameras monitoring these actions, not necessarily at a count level, but even count level can be configured. But the boxes can be done. So any movement in any change, or even if internal goods movement can easily be moved through a camera. So the cameras are recognizing what barcode is going back and forth based on the barcode's visibility on the particular box, and it can automatically update inventory.
Okay, thank you. Is there any special skills required for training or teaching the vision system for acceptance criteria?
As of now, if you want to try with existing algorithm and basically train, there is most of the tools are completely intuitive for you to do on a drag and drop basis. But if you say, hey, I have a very custom product or a custom algorithm, my criteria is not available, then we would advise somebody to learn some programming aspects like Python and some data science to understand and do this. But most of the image recognition use cases, if you're looking at very straightforward use cases, comparison, inspection, most of the algorithms are already there. So 90% of the times there's no programming experience required. But analytical skills are key to measure, calibrate the values, and to interpret the right set of values.
Thank you, Prashant. Is there any X-ray vision type of application to check missing or wrong part inside an assembly?
Yeah, I mean, so this is again doable through an infrared set of sensors, which is available. Even we can look at 3D scan sensors. So these sensors are quite powerful to look at the overall structure and missing components. So again, the analysis can be done in multi-fold. So the amount of data the depth sensing cameras can generate. So using that, we can easily mark any components, as a full. So if the sensor is only once, if the product can be rotatable, we can rotate the product, or we can rotate the sensor itself and capture the 360 degree of the product. So this is doable with a combination of depth sensor and camera sensor.
Thank you. Will it change accuracy if we compare two systems? One is stationary product dimensional checks and the other is component running on conveyor.
Yeah, I think this is a very interesting question, but depends on the numbers won't change a lot, but the training data would matter, right? So if you are moving from a stationary to a rotational, so the data feed, if you are starting from stationary but immediately move, the same training data set will not be effective here. So you need to accumulate a new training data set, you need to create a master training library, and then the accuracies will start around 60%. It'll go to around 95% in a month or 2 months, depending on how much data we are feeding into it. From day one, can you move from stationary to a conveyor setup? The same data will work. It might not. The accuracy will reduce. But if you have been investing on a conveyor data set itself to start, I think then the accuracies will be there. The confidence scores might not be exactly like in the stationary. You might have 85%. On the conveyor, you might get that 85% after 3 months or 4 months, or you need to tweak the algorithm itself because there are so many elements you need to capture for blurriness, you need to capture for vibration, so new conditions to be added in the algorithm. The same algorithm will also not work, but the training data set is plays an actual role here to achieve the same numbers. Yeah.
Thank you. Can we use gain management system?
I'm sorry, I didn't get that.
Or can we use gain or CA, any gain management system?
I'll check with the team if somebody can take that.
Yeah, I'm not really sure. Is it Kane or Crane?
Okay.
So if you can just verify that.
Yeah, we'll check and get back to you on that. Yeah.
Yeah.
It is sugar cane.
Okay, Kane.
Yeah.
Yeah. So what kind of grading needs to be done, or what kind of so it depends on the use case again. If there is a variance, we can do it through image. Do we have a ready-made use case for cane as of now? No, I mean, but we have seen this with foods like tomatoes or oranges or any color code. So if there's a texture variation, there's a pattern variation within cane. We can sugar canes. We can actually do this. It can go in a conveyor and through these are not small components, so air jet will not work. So it can be a mechanical opener itself. We can using that we can actually do the grading.
Thank you. Can a vision system replace a pick sensor?
So pick sensor, it can, I mean, because this is more effective. But if the pick sensor is just guiding information, so this can do a lot more. It can look at the texture, it can look at the speed, it can look at the elements. One single camera, one single photograph captured by industrial camera can give so many depths of information, so it can easily replace. But if you're looking to connect a robot also, hey, okay, the camera sends the defect, but let the robot can go pick it up, and I don't want a manual. So that's again, a robot is an additional investment, but the entire process is automated. So the moment the camera identifies a defect, that is already taken away from the robot. So that's a full automation you achieve, which a pick sensor, which basically tells, hey, you need to pick it up. So this system can help you fully automate that. Replacement, yes, but with some precision, with some business criteria, yeah, this should be a good replacement.
Thank you, Prusha.
Okay, if you don't have any questions, we'll call it a wrap. Please rate the webinar. It helps us do more webinars. We can understand how we are doing on this. If there's something you didn't like, it's something you wanted more to cover, please rate the webinar when you get the rating email. And if somebody's watching this in a recorded way, you can always reach out to us if you have any questions, and we'll be able to basically guide through the machine vision systems and the associated advantages. Yeah, that's it from my side.
Thank you, Prashant. Thank you everyone for joining. I've shared a request to demo button. So you can click there and request a product demo from it. Thank you, everyone.